graduate and PhD student at Fluminense Federal University. After that, he was a postdoc at the same university and in Heidelberg. Nowadays, he's a fellow at the Radboud University, and he is also a professor at the Fluminense Federal University. He works with quantum field theory, in particular non-perturbative methods and renormalization group with applications in quantum gravity. He's also involved in the organization of several initiatives in Brazil involving quantum field theory and gravity. And today, the title of his talk is Space, Time, and Matter under the Microscope. And thank you very much, Antonio, for accepting our invitation. And please go on when you are ready.
Okay, so let me start sharing. So do you see the presentation?
Yes, I can see.
Okay, so let me start by thanking Tiago and Dimitri for the invitation. I'm very happy to give this talk. And today I will, I was asked to give a more general talk. So not talk about a particular paper or a particular result, but more about the general area that I have been working on. And so, okay. So before I start, I have to enjoy the space here and make some propaganda. So recently, it was started an international society for quantum gravity. And if you are interested about quantum gravity and you are at least a PhD student working on this topic or related topics, you can apply for a membership in this website. And recently you had the first meeting of the society, but there are many activities that are being organized for the next years. And these are the list of the founding committee members. And well, I hope that if in case you want to join, just go for it. And also, as Tiago mentioned, I have been organizing 2 series of seminars in Brazil. The first one is a collection of talks, mini courses, and also some outreach videos on essentially GRQC topics. And together with Igor Justo and Rodrigo Sobreiro, I have been organizing the series of talk that also contains a bit of GRQC, but mostly high energy physics and different branches. Let me just move this. And finally, let me introduce my research team at Fluminense Federal University. So currently, the master students that are under my supervision are, I managed to have the pictures of some of them. And more recently, Vito joined from University of Coimbra. So he's still based on University of Coimbra. And very soon also Diego will join as a postdoc with the group. Okay, that being said, so today there was this paper on the archive that I did in collaboration with people here at Radboud University. And if I have time for that, I will mention a couple of things about this paper. But as I said, I'll probably spend more time dealing with the general framework. Okay, so now let me get started with the talk, with the scientific part of the talk. So this is the outline. And my idea is to pass through a general introduction and motivation for quantum gravity. And then I will narrow to the approach that I have been working on, which is the so-called asymptotically safe quantum gravity. But before that, I'll spend some time speaking about the machinery that I use to do concrete calculations. And finally, I will move to this topic, which is related to quantum gravity and matter systems. Okay, so let me start by saying what do I mean by quantum gravity and why do we need quantum gravity, at least, at least some principles behind it. So as we know, we have a very good classical theory of the gravitational field, which is general relativity. And more recently, we have been able to access a wealth of new results and data coming from the LIGO, Vigo, Cagra collaboration. And we are really probing general relativity at the very strong field regimes. And we have an impressive agreement between predictions coming from GR and the data that we have been collecting. Of course, we also, know that the EHT collaboration managed to produce this beautiful picture of a black hole. And as such, black holes are really one of the most intriguing predictions that general relativity provides. And because of that, we know that from GR, black holes have a singularity, a space-time singularity where curvature invariants essentially become singular. And that, this is not a consensus, but we expect that at this regime, when you are going to very short length scales, quantum effects should take place and eventually remove the singularity. So because we see now black holes in the sky, and black holes are very well described by GR, and the description has a singularity, we seem to have a very good motivation to look at quantum effects at very short length scales to remove such a singularity. So on the one hand, we have GR as a classical field theory, but on the other hand, we have quantum mechanics. And in the formulation by Feynman, we know that we have to sum over histories. So if you want to compute the transition amplitude for a given particle to move from a given position state to another position state, you have to sum over all paths that connect these 2 points. And when you transition that to the quantization of special relativistic systems, we automatically get quantum field theory. And quantum field theory is the framework behind the construction of the standard model of particle physics. And again, we have a very impressive intellectual achievement because the predictions made by the standard model, they are in impressive agreement with experiments, and it provides a quantum description of the other 3 fundamental interactions that we know in nature. And in order to construct the standard model of particle physics, one technical principle was used a lot, namely perturbative renormalization. So in order to construct the action that describes the other 3 fundamental interactions, requiring that the theory is perturbative renormalizable was really important. But of course, we also know that the standard model cannot be, the standard model as it is formulated cannot be the final answer for the description of nature. In particular, we still miss a coherent description of neutrino masses, and we still have the dark sector of the universe that, well, it might be necessary to change or to add matter content that's not included in the standard model. And moreover, we still have to include gravity in this story. But before I talk about that, let me just remind for those that are familiar and just mention for those that are not familiar with, that when you quantize a theory, you drive the coupling constants, so the parameters that measure the strength of the interaction, to be scale dependent. So now these parameters, they change with the energy scale. And if now you consider, for instance, the coupling of the quartic interaction of a scalar field, you can now compute the running of this coupling with respect to energy that I'm calling K. And you can see that when you go to high energies, this particular coupling, this quartic coupling, it blows up at a finite energy scale. And this is what is called a Landau pole. The standard model is a theory that contains a Landau pole. So the standard model as well has singularities. It's not, we often talk about the singularities in GR, which are completely different, but the standard model itself has couplings that will blow up at finite energy scales. So if you try to move this energy scale K0 to infinity, you get the so-called triviality problem, because the only consistent solution is to set the coupling to 0. So we are seeing that the standard model and general relativity, they have singularities, and this might require really a modification of those theories in order to remove such singularities. Okay, so as I said, GR and the standard model are really great descriptions of nature in several aspects, but they are not complete in the sense that they still contain singularities which signal that the theory is not valid at the regime where you're trying to apply it. And at the moment, we have two completely disconnected frameworks in the sense that GR is purely classical, and the standard model is does not contain gravity. So the natural question is, can we combine the principles of quantum field theory and general relativity and construct a quantum theory of gravity and matter? So this is the question. And the obvious first step is just to quantize general relativity as we quantized the other theories. So it's just a field theory. We just apply the standard quantization rules. And these standard quantization rules, they are entirely based on perturbative techniques. However, as you probably know, perturbative quantum general relativity is not perturbatively renormalizable. So it means that every order in perturbation theory, you have to include a new term to compensate for the divergences. And this term will come with an arbitrary constant that must be fixed by an external conditions. So this means that your theory will not be predictive at scales that are very tiny, in the sense that in terms of length scales. Because you have infinitely many constants or counter terms to fix according to renormalization conditions. So often we hear that this signal that GR and quantum field theory are not compatible, but we have to be careful, because as I mentioned a couple of slides ago, the standard model itself has divergences in the form of a Landau pole. So in principle, the standard model is also a theory that is valid up to an ultraviolet cutoff. Beyond this cutoff, the standard model, I mean, you are going to hit the Landau pole, and you're going to see divergences in your coupling constants. So although the standard model is a perturbative renormalizable theory, it is not a fundamental theory in the sense that it is valid up to arbitrarily large energy scales. So in this sense, perturbative renormalizability is neither necessary nor sufficient to give you a fundamental theory. Still, you can treat quantum GR as an effective field theory. So it is valid up to the Planck scale. Well, by up, I don't mean really literally the Planck scale, but below the Planck scale. And you can do concrete quantum calculations in this program, and this will give to you perfectly well-behaved results. So this program was pushed mainly by John Donoghue and other people. And for instance, you can compute the quantum correction to the Newtonian potential using this framework. So in this sense, as we have the standard model, which is an effective field theory and gives you a quantum theory for the other three interactions, we also have a theory of quantum gravity, which is the perturbative quantization of general relativity as an effective field theory. So this theory is meaningful up to some ultraviolet cutoff. And when you reach this, the vicinity of this cutoff, the theory is not predictive. But of course, if this was the final answer, we would be happy and just use effective field theory to do calculations in order to compute quantum gravity corrections to the other quantities that we are interested about. But the problem is that the cutoff where we have to introduce in order to make the theory well-defined is precisely the scale where we expect that quantum effects of the gravitational field are important. So in order to have a theory which is fundamental and therefore it can be extended up to arbitrary high energies, we need that our coupling constants are always finite. And as a prototypical example, we have quantum chromodynamics, where the quantum effects drive a scale dependence to the coupling constant, and it goes to zero at large energies. So you see that the coupling here is always finite, and it goes to zero for very large energy scales. In this situation, you can really speak about a fundamental theory that is valid across all energy scales, because you don't hit a Landau pole. So asymptotic freedom, which is precisely the situation where the coupling goes to zero at high energies, is a situation that guarantees that your theory is fundamental. So I will come back to this discussion, but before I want to introduce the functional renormalization group, and the reason behind that is the following. So we know that general relativity is not perturbatively renormalizable, but the question is, can it be non-perturbatively renormalizable? And translating this question to the real question is, what if the gravitational couplings do not develop any divergences across very large energy scales? So we know that the theory is not perturbatively renormalizable, but the physical requirement is that when I compute observables, I need that the gravitational couplings do not blow up. This is the important question. And the mathematical quantities that measure the scale dependence of the couplings are the so-called beta functions. And if you want a way of making sure that your theory will not develop divergences, is to look for a scale invariant regime in your system of beta functions. So if your beta functions, they all vanish simultaneously, then you have a fixed point. And if you have a fixed point, then when your flow hits this fixed point, then it will sit there because your theory will become a scale invariant. And it means that after, if you go above this energy scale, you are not going to develop new divergences. And your theory will be finite for arbitrarily large energy scale. So in the case of asymptotic freedom, the coupling going to 0 is a fixed point, and therefore G equals to 0 is an ultraviolet a fixed point where the coupling vanishes. But of course, in principle, you can have a finite value instead of just 0. And we know very well that if this coupling is finite, and in particular bigger than 1, you cannot trust perturbative approximations. And therefore, you might need non-perturbative tools in order to probe the existence of this fixed point. Okay, so this is an example of a beta function. And here I have the coupling G, and this is the beta function of the coupling G. And you see that the beta function, it hits a fixed point at finite value of G. And therefore, you might think that your coupling, I mean, it is growing with energy, but at some point, your couplings will be attracted towards this fixed point in the ultraviolet. So this is because the coupling is non-vanishing. We call this an interacting fixed point. And the question is gravity a theory that features this interacting fixed point or not? Because this is the physical, let's say, requirement to have finite observables. And okay, let me just introduce some name. If the theory have an interacting fixed point in the ultraviolet, we call this theory asymptotically safe. So the question is gravity asymptotically safe or not? Okay, so let me just explain what is the mechanism behind asymptotic safety. So let's pick Newton's constant, G Newton, and I can attribute to G Newton its dimensionless version, which I'm just calling here a small g. And this is measured now in terms of a cutoff that I introduced in the theory. So I'm measuring G Newton in the units of this cutoff K. So the dimensionless version of G Newton is what enters physical processes. So this is the one that must be finite at high energies. Now, if I compute the beta function of G Newton, the beta function is nothing but the derivative with respect to the energy scale K of the dimensionless coupling. And when you compute that, you get two contributions. One that is 2G plus this contribution here that I'm calling eta G. The first contribution comes from the fact that Newton's constant has a canonical dimension that is non-vanishing. So if you measure in terms of K, then you have this contribution 2G, which comes because of this canonical mass dimension. And eta comes from quantum fluctuations. So if your quantum fluctuations are such that this beta function vanishes, namely the canonical mass dimension balances out the quantum fluctuations, then you are going to find a non-trivial fixed point, which, as I am emphasizing here, might not be small. So you might really need, in order to probe the existence of this fixed point, to go beyond perturbation theory. And you see that Newton constant is a dimensionful coupling, and therefore you always have this canonical dimension contribution here that is essential to balance out the quantum fluctuations. Okay, so at this fixed point, the beta function will vanish, and as I said before, your theory will enter a scaling invariant regime. But this is scaling invariant at the quantum level because it is precisely a cancellation between the canonical mass dimension contribution and quantum fluctuations. So How do we probe such fixed points beyond perturbation theory? Well, one possibility is to use lattice approaches. So it is possible to put gravity on a lattice using the so-called causal dynamical triangulations, a framework, Regge calculus, and also spin forms, group field theory, or tensor models, which are generalizations of matrix models. Of course, these are not equivalent frameworks, but in principle, they correspond to a way of discretizing the path integral of gravity. Alternatively, you might just want to use non-perturbative or functional renormalization group techniques, which is the tools that I'll be using here. So in order to explain in a nutshell what is the functional renormalization group, we start from the path integral in the Euclidean signature. So this is a technical requirement. And I will integrate over my fields, the random variables phi, and I have the classical action S of phi. And the idea behind the functional renormalization group is to implement the idea due to Wilson of the renormalization group flow, where instead of integrating out all the modes of my path integral, I integrate shell by shell in terms of momentum, the fields in my path integral measure. So I divide the field modes by the momentum label of each field, and I integrate shell by shell these fields. Of course, you can do that using a hard cutoff. So you can just integrate out shell by shell in a very hard way, or you can just implement it smoothly by modifying your path integral with a cutoff term. So this cutoff term is quadratic on the fields. So this is a mass-like term. But now I have this infrared cutoff K that tells you the following. If we're taking into account modes below momentum K, then this mass is big, this function R is big enough such that this mass term is big and those modes will be suppressed. When you go to momentum scales that are greater than K, then this mass term must vanish and you are going to integrate out these modes. So you can implement the Wilsonian renormalization perspective by introducing this momentum-dependent mass term. And in order to give you an idea of the structure of this function R, which is just a cutoff function, so it can be arbitrary, it must behave qualitatively in this form. So if this should be 1 here, so if we're measuring momentum p squared in units of k squared, if you are above 1, then this function must go down very fast. But if we're dealing with ratios smaller than 1, then this function must have a large value, and this works as a very large mass. Of course, when you take k, which is the infrared cutoff, to 0, we just recover the standard Euclidean partition function, because this is equivalent to integrate out all the field modes. So you can see that k is some sort of sliding scale that you can start from your ultraviolet cutoff and push, you can bring down the scale k up to k equals to 0. And when you hit k equals to 0, then you have integrated out all your modes. So this is really a separation of modes in the Wilsonian language of fast modes and slow modes. And now we can just implement this idea to any quantum field theory you want. And what is important is that it has a practical use. So in particular, if you introduce your cutoff and define now the analogous generating functions in quantum field theory, you have your generating function of connected correlation functions, but now it is also K dependent because, of course, you still have the master there. And with this, you can define the Legendre transform of this WK, which I will call gamma K. And this gamma K has a special name. It is called the effective average action. And it has a very nice property, which is it interpolates between the effective action, namely the generating function of one particle irreducible diagrams, and the classical action. So if you move down K to 0, this is your effective action, your quantum action. But if you move K to the ultraviolet cutoff lambda UV, this is just the classical action. So K equals to lambda UV is equivalent to not integrating out any modes. And K equals to 0 is equivalent to integrating out all field modes. So you recover the standard effective action that's you learn how to compute in quantum field theory courses. However, gamma K has this general expansion here. So it's a sum of local operators of your field. And in front of these operators, you have coupling constants. And these coupling constants are scale dependent, as we know from quantum field theory. So of course, if you have, so this sum is typically infinite dimensional. I mean, you have infinite terms, your effective action. And these couplings can have, I mean, arbitrarily small mass dimension. Okay, so what is remarkable about this effective average action is that it satisfies an exact flow equation. So you can measure the flow of gamma K. This dt is the derivative with respect to the energy scale K. And this is an exact equation. So you derive this equation without any approximations. And this equation is, it has this one loop structure. So it looks like a one loop equation. But of course, because the propagator that enters here is in terms of gamma, then it contains all quantum corrections. And if you now evaluate this trace of this right-hand side of the flow equation and expand the result in the same basis O of phi that I introduced before, you can just read off the beta functions from this equation. So this equation is really practical because it gives you a way of extracting the beta functions of your theory in a non-perturbative setting. So this is why we like to use the functional renormalization group to do calculations in this framework. So this equation is also called the functional renormalization group equation. But of course, I mean, as I said, in the end, we are looking for non-trivial fixed points. And because we want to define a theory that is valid across all energy scales. But as I said, your effective action will typically have infinitely many terms. So your fixed point will live on a theory space, which is a space of all the couplings, infinitely many couplings. And a fixed point corresponds to a point in this space given by this list of couplings where all the beta functions will vanish simultaneously. So you can say, well, you now are giving me infinitely many couplings to have a fixed point, but all the trouble about renormalizability was due to predictivity. So if you have infinitely many couplings now, of course, you're going to lose predictivity as well. But this is where scaling variance enters. Well, quantum scaling variance enters in order to recover predictivity. So if you have a fixed point, you can linearize the flow around this fixed point. And this will give you this structure here. So you have the linearized flow and you have the derivatives of the beta functions. And the derivatives of the beta functions with respect to the coupling G is what we call a stability matrix. And you can now diagonalize this stability matrix. Well, you can just apply the diagonalization to this equation. And it has this structure here, this very simple structure, where lambda are just the eigenvalues of this stability matrix. So if you solve the previous equation, you get this z, which measures the distance of the point G to the fixed point G star, given by this expression here. And theta is the negative of the eigenvalues of the stability matrix. So we see the following. If theta is negative, z increases towards the ultraviolet, and therefore this is a direction in theory space, which is this abstract space, that is repelled by the fixed point. So this is what we call an irrelevant direction. So if you want to hit the fixed point, then you must impose that Ci is 0. This is an integration constant. However, if theta is positive, then this z will decrease towards the ultraviolet, and this will be automatically attracted to the fixed point. These are so-called relevant directions. And therefore, C is a free parameter. So relevant directions are free parameters, and irrelevant directions are, you fix this integration constant to 0, and therefore they are not, if you go towards the infrared, they are predictions of your theory. So it means that if you want to have predictivity, you better have a finite number of relevant directions in your theory space. So this is an illustration of the fixed point, and this surface is the surface is spanned by the relevant directions. So if this surface is finite dimensional, then your theory is predictive. Okay. So now let's move to the application of these techniques to asymptotically safe quantum gravity. So in the seminal work by Martin Reuter, in order to deal with gravity, because gravity is complicated, we have to introduce the background field method. So you split the metric as a background metric. So this is a fixed background metric and fluctuations around that. But don't confuse that with small fluctuations. So these can be violent fluctuations of the background metric. And this background metric will set the scale. So now you can label your field modes in terms of eigenvalues of the Laplacian operator defined with the background metric. And you also have to introduce the cutoff function, which is given by this expression here, which is quadratic on H, which is the quantum field now. And as you can see, so your theory is a theory of metric. So you have this field, but when you split in two fields, you ensure that the theory is a theory of just the metric if split symmetry is preserved. And split symmetry is a symmetry that tells you that if you add epsilon to the background metric and subtract the same epsilon of H, then your full metric is invariant. And the regulator breaks this symmetry because you treat the fluctuations and the background on a different footing. But that's a technical thing that I don't want to enter at the moment. But in gravity, you also need to gauge fix. And therefore, you have to introduce the gauge fixing term, Fadeev Popov ghosts, and all of that. Okay, so now that we have a concrete framework, let's try to use that and search for fixed points with the flow equation. the first thing is that the flow equation is exact, but of course we cannot solve that. So what we do, we choose truncations for the effective average action and use these truncations in order to look for fixed point candidates. And the task is to enlarge these truncations and take into account more and more operators and see if the fixed point that you found is stable or not. So if I choose the simplest truncation, which is the Einstein, given by the Einstein-Hilbert action, where you have a cosmological constant and Newton's constant, and of course, gauge fixing and ghost terms. If you move now to the dimensionless versions of the couplings, you can compute the beta functions of the dimensionless cosmological constant and Newton's constant. And because of the non-perturbative nature of the functional renormalization group, you see that this is a non-polynomial function. And therefore, if you expand now this in powers of g and lambda, you're going to have infinitely many terms of lambda and g, and infinitely many powers of lambda and g. So if you look for a fixed point now of this very simple two-dimensional system, you are going to see that there is a fixed point. So there is lambda star and g star that makes these two beta functions to vanish simultaneously. And if you compute now the eigenvalues of the stability matrix, you see that this two-dimensional theory space has two relevant directions. So you might worry about when you go to infinite dimensional theory spaces, you might worry that the number of free parameters will grow with the dimensionality of your truncation. However, if you enlarge truncations now, if you introduce more and more geometric operators, you see that, so this is not the most refined results, but I decided to put my own results with my collaborators, Gustavo de Brito and my student Arthur Vieira, because of course, I mean, these figures I will explain better. So if you enlarge your truncation, for instance, by introducing f of r type operators, for instance, if you introduce up to r to the 20 in your truncation, you see that your fixed point values, they oscillate a lot for small truncations, but you see an onset of convergence of the values of the fixed point when you go to larger truncations. And the same happens with the critical exponents. So here I have two positive critical exponents, which stands for the relevant directions. So you see that I'm enlarging theory space by operators now up to R20, but the number of positive directions, which are the important ones for predictivity, remains finite. And of course, because this is a finite dimensional truncation, but more importantly, they are much smaller than the dimension of theory space. Of course, I just have to mention that in this case, in this truncation here, I'm not introducing the cosmological constant. This is a calculation in the so-called unimodular setting, but this is just a technical remark. If you introduce the cosmological constant, you have now an extra relevant direction. Okay, so I have tried to convince you so far that it might make sense to look for a fixed point, a non-trivial fixed point in quantum gravity. But of course, we know, for instance, in QCD, if you compute the beta functions of the gauge coupling for a number of, if you introduce a number of fermions smaller than 16.5, your theory is asymptotically free. But if you introduce more than 16.5 fermions, you lose asymptotic freedom, and your theory now has the opposite behavior, namely the coupling constant grows with energy. So the obvious question is, if we introduce now standard model degrees of freedom in our game, can we mess up with the fixed point, the gravitational fixed point candidate? So this is, of course, a very important question, because we know that matter exists, and you cannot avoid the interaction of matter and gravity. So if matter is such that it destroys the gravitational fixed point, then you might just stop doing this asymptotic safety program. So again, I will quote my results with my collaborators, that, for instance, if you introduce, again, this is in the unimodular setting, so I will not enter in the technical details, but here you introduce n phi scalar fields and a vector fields and n psi fermionic fields. And you see that if you don't introduce any matter degrees of freedom, you have a fixed point. Now, if you introduce the matter content of the standard model, you also get fixed points. You see that here you don't find, but this is in this hybrid semi-perturbative computations that I don't want to enter again the details, but at least in the self-consistent truncations, we do get a fixed point. But of course, as I said in the beginning of this talk, you might want to introduce standard model degrees of freedom and minimal extensions of it. For instance, 3 right-handed neutrinos. And again, you are going to get fixed points in this situation. But for instance, if you want to modify the field content of the standard model by introducing the field content of the minimally supersymmetric standard model, we do not find a fixed point. So it tells you that, for instance, if you take seriously these results in terms of the truncation that we used, and of course, this must be tested against improvements of the truncation. This means that if you find in LHC surveys or other accelerators, if you find evidence for the MSSM field content, then this program might be in danger. So this is just an example of a way, a complete indirect way of testing the consistency of a quantum gravity approach using particle physics data. Of course, as I said, this might require a lot more of understanding of these approximations that we did. But this is, I mean, in terms of technical test, this must be really a way of making restrictions about the quantum gravity approach you are looking after. Okay, so now, so I promised to myself that if I didn't have time to talk about the paper that appeared today, I would not talk about, but I think I still have a couple of minutes, right?
Yeah.
Okay, so let me just make a couple of remarks about this paper that appeared today, which is the following. So when you couple matter to gravity, you have a lot of subtleties. And in particular, if you just introduce a kinetic term for a scalar field, for instance, that in flat space we'd call this a free theory, you see that you have the square root of the determinant of the metric and the inverse metric multiplying this kinetic term, well, this bilinear term. And now if you expand this determinant of G and the inverse metric using this background field method, you generate infinitely many vertices between graviton fields. I'm calling H now as gravitons, but don't take that too seriously. And scalar fields. So your free theory is not free when you go to a dynamical metric. So you have infinitely many graviton scalar vertices. And I represent these vertices here, where this double line is represents the gravitons, and the thin line represents the scalar fields. So those vertices, they will also carry over the global symmetries of the scalar kinetic term. And what are the global symmetries of the kinetic term? So I don't know why these arrows are here, but they were supposed to be here pointing to these boxes. But anyways, the first one is reflection symmetry. So if you take phi and replace it by minus phi, your kinetic term is invariant. So all these interactions that you generate from the kinetic term will be Z2 symmetric. And you also have shift symmetry. So if you take phi and replace by phi plus a constant, the kinetic term is still invariant. And therefore, these interactions will be also shift symmetric. So with these vertices that you generate, you can now build this type of effective interactions where you have external matter legs and internal graviton loops. So you see now that you have a self interaction of a scalar field that is, first of all, shift symmetric. So if you perform this transformation, this interaction will be invariant, and Z2 symmetric. And another important remark is that we can also have, in principle, the standard scalar potential. So you can introduce the standard polynomial potential in your theory, but this scalar potential might not have the symmetries of the kinetic terms, and typically they don't. I mean, of course, typically, if you have a Z2 symmetry, you choose a scalar potential to also have Z2 symmetry, but not shift symmetry. And if you include just a scalar potential with standard polynomial interactions, studies with the functional renormalization group suggest that those interactions, namely the standard polynomial interactions, they have a Gaussian fixed point. So a Gaussian fixed point means a trivial fixed point. So they reach zero at the fixed point. However, those effective vertices that are unavoidable, they are generated by quantum fluctuations, they will be shift and reflection symmetry invariant. And you can argue that interactions which have these symmetries, in particular shift symmetry, will not have a trivial fixed point. So they must have an interacting fixed point. And just to give you a flavor of that, this is an example of shift symmetric interaction. So it's quartic on the fields. All the fields comes with derivatives. This ensures shift symmetry. And you have this coupling CK, which is the coupling associated with this interaction. So when you compute the beta function of C, or the dimensionless version of C, you can separate two types of contributions to this beta function. One that is independent of C, and this comes because of the structure of the kinetic term. So the kinetic term will contribute with this function F that just depends on the gravitational couplings and is independent of C. And of course, the self interaction will contribute to these beta functions, and other interactions can also contribute to this beta function. So if this term is completely independent of CK and you have a gravitational non-trivial fixed point, namely G star different from zero, then if you set C to zero, this contribution can vanish, but this will not vanish. And therefore, you cannot have a Gaussian fixed point or a trivial fixed point for CK. And that's the reason behind the presence of non-trivial fixed points for this type of couplings. So this is an example where when you don't have gravity, then your coupling, your shift symmetric coupling, has a Gaussian fixed point and might also have a non-Gaussian fixed point depending on the dynamics. And when you turn on gravity, the Gaussian fixed point, because of the structure of the kinetic term, is shifted to a finite value. So this is the shift that I showed here due to this contribution here. But if quantum gravity fluctuations are too strong, then this curve might be shifted in such a way that your beta function will not have any zeros anymore. So this is a highly non-trivial test because you have to check that these interactions that are shift symmetric, they have a fixed point, a non-trivial fixed point, in order to have a consistent, asymptotically safe theory. This is highly non-trivial. I mean, if you really check that, and quantum fluctuations coming from the gravitational contributions are too strong, then this scenario, when you couple matter to gravity, might be completely inconsistent. So I'll just cut this story short, and you can also introduce non-minimal terms, non-minimal interaction terms that are also shift symmetric. And again, all these terms are generated by quantum fluctuations. So you cannot avoid the introduction of such terms. And again, because they are shift symmetric, all these contributions must have a non-Gaussian fixed point. If you introduce, for instance, this term, it was verified by Astrid Eichhorn, Stefan Lippold, and Vedran, that you still have a fixed point when you introduce this non-minimal coupling. However, more recently, Gustavo de Brito, Astrid Eichhorn, and Rafael dos Santos, they have analyzed a truncation of the effective action that just contains these quartic self-interactions. And they didn't find a fixed point. And this, I mean, this is really a result that came out. And therefore, they interpreted that as a necessity of having different species of fields in order to generate a fixed point, which is, of course, very nice, because we know that our universe does not contain just a scalar field. But in this paper that appeared today, we analyzed a truncation that includes more operators than just the quartic self-interaction, but also the complete set of non-minimal interactions with a bilinear of scalar fields. So you have this Ricci tensor and the Ricci scalar. And if you leave, well, these are technical requirements, but our results agree with what was found previously. For instance, if you include just these quartic self-interactions, as in the previous work that I mentioned, we also don't find a fixed point. But when we include now, so when you include, I also mentioned that when you include just this term, you find a fixed point, and we also verified that. But when you include this guy, you don't get a fixed point. And finally, when you introduce these three couplings, namely these three interactions, we do find a fixed point. So this is really a non-trivial interplay between these non-minimal interactions and this self-interaction that is shift symmetric. So here is just a result showing that this is just a notation for the interactions that we included. And we see that this is the complete truncation where we introduce the non-minimal couplings and the self-interaction. You see that in all truncations that we find a fixed point, we have a reasonable agreement between scaling exponents and the gravitational fixed points. Of course, we have to enlarge this truncation in order to confirm if these results are really converging or not. And finally, just as a technical remark, we have also showed that actually, if you have a shift symmetric action, gamma k, effective average action, then it is consistent with the RG flow. Namely, if you now move the RG scale k, you are always confined to the subspace of shift symmetric interactions. And therefore, we really have to look for the non-trivial fixed point in this subspace of shift symmetric interactions. So shift symmetry is preserved along the flow. And this is non-trivial because typically coarse graining techniques will break symmetries of your theory. So our results suggest that scalar tensor theories can be asymptotically safe, and therefore they can really be UV complete without extra structures. Of course, you can ask, well, does it mean that the low energy effective field theory that you get from this UV complete theory is consistent? The answer is not necessarily. And in particular, you have to apply consistency checks. For instance, recently there is this program of positivity bounds that is being explored, but also this swampland-like conjectures that now we can apply to a consistent quantum gravity framework and check whether they are satisfied or not. And then it would be nice because typically these swampland conjectures, they are claimed to be valid for all quantum gravity approaches. And this is an alternative quantum gravity approach to string theory, for instance, where we could test if the swampland conjectures are applicable or not. So as my conclusions, I have this huge list of things, but because I think I already talked a lot and I'm slightly over time, I'll just leave this slide here and stop. Thank you very much.
Thanks a lot, Antonio. Very nice. And I think now we can open to questions. I don't know. Maybe. Okay. Okay. So Dimitri, please, you can.
Yeah, thank you very much, Antonio. It was a very interesting and very pedagogical talk. So I have a couple of questions. One of them is about the flow equation. You said it's an exact equation. So my first doubt was whether, I mean, this is a practical equation and you can do explicit calculations. And what if, for example, if you, even if you consider theory which is cut off, so maybe you can comment on that. So apparently you are able, even with some quite complicated cut Lagrangians, you can do the calculations.
Yeah, so the flow equation can definitely be used for explicit calculations. And for instance, it has been used widely in statistical mechanics systems and now gravity. And the point is, as any other non-perturbative technique for quantum field theory, you don't have necessarily a systematic way of approaching the problem a priori. So you have to investigate these truncations that I mentioned and learn from the system in which direction it stabilizes better. And therefore, you can make new ansatz for your truncations and check whether this principle that you have invented according to your results, if this is confirmed or not in practice by your explicit calculations. So recently, not recently, but in the last 10 years, I would say, the flow equation was used, for instance, to compute scaling exponents for the Wilson-Fisher fixed point. And after, a couple of years, people spent trying to understand in which direction you should go in theory space, we have now results that are quantitatively competitive with, for instance, the conformal bootstrap. Moreover, people are doing non-perturbative calculations for QCD propagators, for instance, for the gluon propagator, quark propagator, ghost propagator, which fit very well, they are even predictions actually, very nicely with gauge fixed lattice simulations when you go to the very deep infrared. So I guess the challenge is you need to find a guiding principle to construct your truncation. And when you start doing calculations in completely dark, you don't have this principle a priori. But after doing explicit calculations, you start learning in which direction your theory stabilizes.
Okay, you also mentioned some an alternative approach, which is lattice calculation. Some people do. So what are the predictions what is the insight that you get from the lattice calculations in gravity?
Yeah, so for instance, the one that I know better is the so-called causal or simply dynamical triangulations, where you just discretize the path integral of gravity using the Regge action, and you just do Monte Carlo simulations. And what happens is that they of course want to find a second order phase transition to find a continuum limit of this theory. And they do have evidence for that. And this, in order to have a phase transition, you need a fixed point, right? This would be the analog of the calculations that I'm showing here in terms of lattice calculations. So they do have evidence for a second order phase transition, which in this language that I presented is equivalent to the existence of a fixed point, a non-trivial fixed point.
This is for a specific theory or for some models that are compatible with your models?
So this is really discretization of GR. So your Boltzmann weight, if you wish, is given by Einstein-Hilbert, but discretized, of course, because you're putting in a lattice. And they find evidence for this phase transition. But of course, as any non-perturbative calculation, we can only speak about this evidence for, because I mean, you cannot really prove mathematically that there is this phase transition yet, at least.
Okay, thank you.
Welcome.
So Fabio, please go on.
Yes, Thiago, thank you for the word. Antonio, congratulations for this nice way to talk about your area of research. Pretty physics is very clear in the way that you speak. Look, could you come back, please, for your graph about the critical exponents?
You mean this one?
No, the first one.
This?
Yeah, this.
Yeah.
Look, there is some physical reason, because in the major part of your truncation, you have more data in the negative part, right? Mm-hmm. There is some physical reason behind this.
No, I mean, what happens is that you compute these critical exponents when you enlarge the truncation, and it turns out that when you enlarge the truncation, all these operators, which are already relevant when you turn on the quantum fluctuations. So this is essentially telling you that the system is, in a certain sense, semi-perturbative or near-perturbative, because canonical power counting seems to be a good way of labeling which couplings will become relevant and which couplings will stay irrelevant. So these two relevant directions. They correspond to essentially Newton's coupling, the cosmological constant, which I do not show in this plot, but the other one is R squared, so the operator R squared. But now all the other operators, R cubed up to R20, they are all irrelevant. So they are all predictions of the theory.
Right. Thank you for your answer.
Yeah.
So when you mean polynomial truncation, this general polynomial in R, in the Higgs, you are taking very...
Yeah, so here, I mean, for the numerical calculations, you have, of course, to cut this degree of the polynomial. But I mean, there are calculations that were done recently where you have more than 100 powers of the Ricci scalar. So the truncation itself can be, you can write and just have a closed form of computing the, let's say, the beta functions of the next couplings. But when you do the numerical calculations, you should, well, of course, in principle, you can compute for any couplings, but you need computer power, memory, and also a clever way of extracting these fixed points, because it might be that you have also spurious solutions that are zeros of the truncated beta functions, but are not candidates of fixed points, because well, when you truncate a polynomial, you can get several roots that will not persist if you go to next order.
Okay. Okay. So yeah, please, Edson, go on.
Oh, thank you, Antonio, for your talk. I would like to make a question. Is about the role of Einstein-Hilbert action in this approach. Is there any kind of special feature about Einstein-Hilbert action, or just a matter of truncation?
Yeah, so this is an important question. In this way of doing the calculation, you make an ansatz for the effective average action, which is not the classical action that will enter in your Boltzmann weight. So in principle, you have really, let's say, the concrete way of doing things is to compute gamma k and flow to k to infinity, which will be equivalent to your classical action. This would be the way of discovering what is the classical action that should be present in your Boltzmann weight. However, in terms of truncations, as this plot shows, for instance, in this f of r type of truncations, you see that the only new coupling that will enter in terms of relevant coupling is the r squared coupling. Okay, so it means that you don't need to include, or it seems that you don't need to include very complicated terms in your effective action to reconstruct what are the relevant couplings. But I think the correct or the safe answer to your question is to say, well, I don't know what will be the classical action that will enter in your path integral, because this would require to solve the flow equation and go up to k equal to infinity. So what I can say is that it seems that introducing some interactions additionally to the Einstein-Hilbert ones seem to give all the essential ingredients, if you wish, in terms of the scaling properties of the fixed point. But I'm not in a position to say that, of course, just by, let's say, dimensional analysis arguments, and I mean, if you go to a very naive flow of the couplings, you're going to see that when you flow towards the infrared, so towards lower energies, you recover general relativity. So this at least this is not a problem in this approach. I mean, you don't have to do much in order to it's essentially a built-in ingredient in this approach to recover general relativity when you flow towards the infrared.
Can I have a time for another question, if I could? Can I ask
please.
another question?
Yeah, yes, please.
When you consider coupling with matter, did you consider a coupling the type of psi r phi 2? Psi
Yes.
is the minimum, is the curvature coupling?
Yes. So they would belong to this scalar potential. Well, of course, they are not standard. Okay, they are not standard scalar potential interactions, but they are not shift symmetric interactions. So they will be in this class of interactions that will have a vanishing fixed point.
Yeah, because as the coupling parameter is a free parameter, your way of doing things might be a way of choosing values for the coupling parameter.
Yeah, that's correct. I mean, in principle, if you introduce this coupling, and for instance, if you have a more complicated theory than just a scalar tensor theory, but you also have, for instance, you couple two vectors or spinors, and you compute the scaling exponent of this interaction that you mentioned, r phi squared. And if the scaling exponent is negative, then this is a prediction of the theory. Mm-hmm. So you can write this coupling in terms of other couplings that are the external parameters that you choose.
Mm-hmm. Okay. Thanks a lot. Nice. Thanks.
Welcome.
Okay, I think there are no further questions. So thanks a lot, Antonio, again. Thanks everybody for participating, and see you in the next seminar.
Thank you very
Bye.
much. Bye-bye.
Bye.
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 Thank you, Antonio.
See you.